Hello everyone and welcome to the next lecture video of this case of matter. For today we are going to look at what is the Dalton's partial pressure followed by the kinetic theory of gases. Very important for a theoretical examination. Okay, what is the equation that has been given? There are a lot of things that we need to complete for today. So there is a lot to know, a lot to discuss and a lot to understand for today. So let's start without ado in time. So the first thing that we need to accomplish for now is going to be the Dalton's partial pressure. Okay. Now in order to understand the Dalton's partial pressure, let us first assume that we have a container. And in this particular container, let's say that this particular container is going to have a mixture of gases. Okay, now when we have taken a container, let's say that this particular container is sealed properly from the top by the help of a particular piston. We are going to pack it. Okay, now let's say that this is the container as what we have. Now in this particular container, let's say these are the gas molecules. Let's say this is a gas molecule of A. Alright, so these are the gas molecules of A. And in the same container, let's say that we have the other gas. Let's say this particular gas as what we have over here. Let's say this particular gas is a gas B. Condition is that the gas A and the gas B are not going to be reactive. So, in short, we are taking a mixture of non-reactive gases together. Okay, let's say that we have a third type of gas in the same container, and let's say this is the gas C as what we have here. Let's say this is a gas C. Okay, so Dalton's partial pressure says that whenever a container has a mixture of non-reactive gases, so these non-reactive gases, what they do, they generally go on. What they will do, they are going to have pressure induced on the walls of container. Okay, so let's say the total pressure that has been induced over here. Let's say that particular total pressure is given as P of total. Okay, so according to the Dalton's partial pressure, okay, what is this is that the total pressure exerted by the mixture of non-reactive gases is going to be equal to the partial pressure of individual gases. Now let's understand this particular terminology here as what I use is the partial pressure of individual gases. Okay, now let's zoom in at this particular condition and let's see what we have. Let us say that this is a piston. Okay, let's say this is a piston over here. And there are several molecules, out of which one of the molecules that I'm going to take it over here. Okay, now this particular molecule, of course, this is a B molecule, let's say. Okay, now there is a second molecule. Let's say that the second molecule as what we have is this A molecule over here. There are several more gaseous molecules of A also over here. Okay, and let's say that this is the third type of gaseous molecule, and that gaseous molecule is over here, and that is the green, that is the C1. Correct. Now, all of these are going to go and colloid, of course, on all sides of the container wall. Now, when it colloids, it is going to generate pressure. The total pressure is equal to the pressure exerted by this particular molecule. That is, let's say, the molecule B, plus the pressure that is exerted by this black molecule, that is nothing more than A, plus the pressure that has been induced because of this particular C. Correct. So, the total pressure is equal to the pressure exerted by the individual molecules, provided these particular gaseous molecules are non-reactive in their nature. So, therefore, according to the Dalton's law of partial pressure, the total pressure is equal to the pressure pressure exerted by the individual gases. That is the partial pressure of individual gases. And that is called as the Dalton's law of partial pressures. Okay, now if we do take it in the form of a statement, we are going to have it as the total pressure, exerted by the mixture of non-reactive gases is equal to the sum of partial pressures of individual gases. So, whatever the gases, the gas molecules, individually they are going to induce a pressure, that particular pressure exerted by a single molecule of a type of a gas is called as a partial pressure of a gas. Okay, and that is what he is saying, that the total pressure of a mixture of a gas is equal to the sum of the partial pressure of individual gases. Okay, now what is the main application? What is the main help of this? We try to understand that. Now, in the application point of view, it will help us to understand what is the partial pressure of a dry gas. Now, in order to understand this terminology as a dry gas, let's understand that, let's assume that we have a particular container. Let's say this is a container as what we have here. Okay, and let's say in this particular container, we are going to take a simple liquid, let's say a simple liquid such as water. Okay, so when I'm going to take over here water, of course, this particular water is going to have certain amount of the water vapor over here. We do agree with this particular fact. Okay, let's say this is nothing more than the water vapor. At the same time, as this particular container is going to also have certain amount of gases over here, the air over here, right? Now, let's zoom in. Let's understand what is going to happen in this particular area. Let's try to understand this particular. So, if I'm going to take over here, this is a liquid as what we have seen, and let's say this is the water vapor. Let's say these are all these water vapors. Correct. Now, what we have the second point, we have also the air molecules over here. Let's say these are the air molecules as what we have. Now, when we observe the pressure that is being generated on the surface of this particular liquid, this particular pressure is because of the two things that are above the liquid surface. One, as what we have these particular water vapors. The water vapors are going to induce pressure on the surface of this liquid. Correct. At the same time, we have the second one. The second one who is going to induce the pressure, and that is nothing more than the air molecules. Correct. So, now here, if we see the total pressure that is going to be exerted is equal to the pressure of the air, okay, or we can say as the pressure of the gas, plus the pressure as what has been induced by the water vapors. Let's say this is because of the water vapors. Correct. Now, if you do see the pressure exerted by the water vapor over here, it is also called as aqueous tension. So aqueous tension is denoted by the letter as F. Okay. So aqueous pressure is nothing more than, it is the pressure as what we have that has been exerted, pressure exerted by the water vapors. Okay. Now, if you do see that what is the pressure that has been exerted by the gas, a simple dry gas, then we can give it as, therefore, pressure of the dry gas. Okay, that means except for the water vapors is equal to, that is nothing more than the total pressure minus the aqueous tension. Now, usually what happens is, for the competitive exams, certain questions have been given on this particular basis. So we have to remember this particular equation. It's quite important. Okay, so therefore, pressure of gas, that is nothing more than partial pressure of gas, is equal to total pressure minus aqueous tension. So this is the use of the Dalton's law of partial pressure. Okay, so this is one of the context as what we have to remember. Okay, so let's go for the next concept. Moving forward with the next one, and that is going to be the important one, and that is the kinetic theory of gases. Okay, now this kinetic theory of gases was being put forward by the three important scientists, and they were by Maxwell, Boltzmann, and Clausius. Okay, so they put forward certain statements which we call them as postulates. Okay, now there were certain postulates which were being put forward by them, and we need to discuss one by one out of them. Now, the first statement which was being made for by them was the gases contain a large number of minute particles, and these particular minute particles were nothing more than molecules. They call them as molecules. Okay, the most important factor. The second statement which was being given by them was the molecules are in continuous random motion and during this particular random motion what happens? During these random motions they collide with each other and also to the walls of container in which they are taken. Okay. Now, going forward with the third point. Now, in the third point, they say that here is where a particular variation occurs. Okay, so we'll mark it over here first. Okay, because this is one of the important factors which you'll understand in the later studies. So the third point says that the volume occupied by the molecules is negligible Okay, very important. He says that the particular volume that has been occupied by the molecules is negligible when compared to the total volume occupied by gas. Okay, so this is one of their statement which is actually a bit wrong. You will understand it in the future studies. Okay, the fourth point says that the intermolecular forces of attractions of attractions which has been present between the two molecules. Again, they say that this particular intermolecular forces of attractions are negligible. Again, one of the most important points that has been put forward. Again, this particular point is going to be wrong. In our future studies, we'll understand about this. So, the intermolecular forces of attraction between the molecules is, again, they call it as negligible. Okay. Now, the fifth point. The fifth point says that whenever the two molecules are going to come forward and they are going to collide, okay, this collision is perfectly elastic. What they do mean by elastic is that there is no gain or there is no loss of energy. But whenever these particular molecules do collide, when let's say that these are the molecules of gases, whether they collide among themselves or whether they collide with the wall of the container, what is going to happen is as they collide, they simply just pass away. They just come close to each other, they just collide and they just go off. During this collision, there is neither a transfer of energy. Okay. Now, there is no gain, there is no loss of energy. The energy remains constant. So, they said that the collision between the molecules of gases are of container are perfectly elastic. Okay. Now I already told you what is meaning of elastic. The elastic means there is no going to be no gain or no loss of energy. If the energy is going to be transferred, the overall average amount of energy remains constant, and that is what they call it as perfectly elastic collisions. That is a collision between either two molecules or between the molecule and the walls of a container that remains absolutely elastic. Okay. Now the next one says that is the average the average kinetic energy of the gases is directly proportional to absolute temperature. Okay, coming forward with the seventh point. Now, in the seventh point, they say that whatever the pressure, let's say that this was a container, let's say this is a container. Okay, whenever these particular molecules are going to go and collide to the walls of the container, they are going to generate the pressure. That means the pressure is exerted when the molecules of gas collide with the wall of containers. Okay, so this was all about the kinetic theory of gases. Now, taking all of these particular points, they came across a particular expression, and that particular expression was given as pressure into volume. P refers to pressure, V refers to the volume of the gas, is equal to 1 over 3 mNc squared. So where P is nothing more than the pressure of the gas, V is the volume, M is the mass of gas, N refers to the number of molecules, and finally what we have is a C. C is the root mean square velocity. So remember, C is root mean square velocity. While we have the other terminologies such as M refers to the mass of the gas that has been taken in a container, while N is how many number of the molecules that we have, followed by C, that is the root mean square velocity. Correct. So this was all about this particular kinetic theory of gases. Okay, so please do make a note of this particular expression, that is PV is equal to 1 by 3 mNc square. We'll see you in the next concept. So, coming to the next section, and that is going to be the ideal gases. Now, ideal gases are those particular gases which obeys the condition P into V is equal to nRT, and that is nothing more than an ideal gas equation. Okay. Now, any gas that is going to obey PV is equal to nRT at all the conditions. Condition is at all the conditions of pressure and temperature. Such kind of gases, we call them as an ideal gas. Now, there was an experiment that was being performed. An experiment which was performed at higher temperatures, so at higher pressure and lower temperatures. Okay, now when this experiment was performed at this particular condition, that is the condition such as higher pressure and at lower temperatures, what did they find out was there was not a single gas. No gas is going to follow or obey the ideal gas equation. Okay, now due to this particular condition, we can say that an ideal gas is nothing more than, it is just a theoretical concept. It's just a theoretical concept. We cannot expect any single gas which is completely ideal. Of course, there are few gases which will exhibit a nearly ideal condition, but there is no such gas as an ideal gas. And on the other hand, if we observe, if this particular experiment was being conducted at the conditions such as at lower pressure and a higher temperature on the other hand, okay, at this particular condition, the gases which obey the ideal gas equation. Okay, now any gas that obeys an ideal gas equation at a condition of a lower pressure and higher temperature. Now at this particular condition, we call this particular gas as nothing more than a real gas. The gases which exist, these particular gases, we call them as the real gases. Okay, now further we need to understand that how this particular deviation occurs. Okay, so therefore deviation deviation of real gas from the ideal behavior. Okay, now in order to understand this, we need to go back to our first law. The first law what we had already studied, and that first law was the Boyle's law. Correct. So therefore, if we consider the Boyle's law, so from Boyle's law, from the Boyle's law, what we are going to have? We have an expression that is P into V, that is the pressure into the volume. This particular product remains always as a constant, right? So, if we do plot a graph, if we do have a plot a graph over here, and that of a product of pressure into volume, let's say over here, pressure into volume and versus the volume. So when we do plot a graph, if this particular gas was an ideal gas, that means if it goes with the condition as a product of P into V, it remains as a constant, then we would get a particular straight line. Okay, and if we do get a straight line, that means this particular product would be constant. Now, this condition will show us an ideal behavior, or we can also say it as an ideal gas. Okay, now, but when we do actually plot a graph for the real gases, okay, so when we do plot a graph for a real gas, what we understand here is the gases which have the lower mass such as, you can say as helium. Okay, this helium, as we plot among the PV versus the volume, it shows a continuous increase. Okay, so this was showing us a continuous increase, such as here, that this increase is going above the ideal behavior, correct? So we would call this as a positive deviation. On the other hand, if we do plot a graph for the gases like hydrogen, so again it is going to show us a positive deviation. Okay, now when we do plot a graph for a heavier gases, heavier molecular mass gases, what we have? We have such as methane gas, we have carbon dioxide gas, correct? So in such kind of cases, what it has to happen was, first, these gases would show us a negative deviation. It would reach a particular point and then slowly it is to start to raise, such as in the condition of methane, and similar condition was shown with respect to carbon dioxide. So, heavier gases, first they showed negative deviation and followed by a positive deviation was been observed. While the lower gases or the lower molecular mass gases, what it used to show us was a continuous increase. That means it was showing us a continuous positive deviations. Okay. Now, then the next concept we need to understand that why there is a deviation. Now we have understood how these particular real gases are deviating from their ideal behavior. In the next concept we shall understand as why there is a deviation of these real gases from the ideal behavior. Alright, so now let's understand what are the actual causes for the deviation. That is the deviation of the real gases from ideal gas, or we can also say as the deviation of the real gases from an ideal behavior. Okay, so according to Van der Waals, what he says is there are the two postulates in the kinetic theory of gases itself which are not correct. So therefore, according to him, there are two postulates which are absolutely responsible for this particular deviations. Okay, and if we do correct these particular postulates, yes, of course, even the real gases will tend to show you an ideal behavior. Okay, so according to him, the two postulates are, the first postulate, which is not correct, is going to be the volume occupied, by the molecules is negligible when we compare to the volume of gas itself. Okay. And the second point, what he says is the intermolecular forces of attractions. These particular forces of attractions, according to Boyle, again, is incorrect because they say that intermolecular forces of attractions are negligible. Again, he says that even this particular point is not correct. Now, these particular points do hold correct if the conditions are such as, if we do consider lower pressure and higher temperature. Now try to understand this. At the higher temperature, what we are doing there is that we are supplying in the energy. As these particular molecules are going to get that energy, these molecules will start moving in a random motions. Correct? The volume actually expands there. So at that particular condition, at a very huge volume, a volume which is occupied by a single molecule, yes, it becomes negligible when we compare to the total volume of the gas. Yes, at this particular two conditions, these are correct. It holds perfectly correct. But when we have a condition such as higher pressure. Now, when we increase the pressure, that means the distance between the two molecules is going to absolutely decrease. Correct. Now, at the higher pressure and lower temperature. So again, we are decreasing the temperature. As we decrease the temperature, it has a direct effect on the kinetic energy. So you decrease the temperature, kinetic energy between the molecules is going to decrease. As the kinetic energy decreases, the molecules will come closer to each other. So at that time, intermolecular forces of attractions holds good. So therefore, what happens there? Intermolecular forces of attraction increases. Again, that time the volume which is going to be occupied by these molecules, of course, they will become significant. So at this particular condition, the conditions such as the higher pressure and the lower temperature, these 2 points will not hold correct. Okay, so therefore, in case if these particular points were correct, let's say if these particular points were correct, then in the first condition, if the point 1, that is the volume which is occupied by the molecules, is negligible, if that was a correct point, then the calculated value, the calculated volume, we can say, okay, that is experimentally once, should be equal to the theoretical volumes, such as of that of the ideal gases. So in short, they say that if this particular point is correct, if the volume that is occupied by the molecule is negligible, it is completely negligible when we compare to the total volume of a gas. That means whatever the gas I am going to take for the experimentation, that volume should be equal to the theoretical volumes, that is that of the ideal gases. Okay, at that particular temperature, at that particular pressure. In short, they are saying like PV is equal to nRT. Now, second point is that if the point 2 is correct, that is intermolecular forces of attractions are negligible. Okay, there is no force of attraction. If that point is correct, then the gases They should not liquefy if this particular point is correct. Okay, so therefore, if these 2 points are correct, then these 2 points will be correct. But we cannot have this, neither we have this. Of course, when you generate the pressure, what will happen? The gases usually are going to get liquefied. Correct. Secondly, there is always a deviation between the calculated volume and that of the theoretically calculated volumes. Okay, experimental volumes and theoretical volumes, there is going to be certain amount of differences. Okay, now the next concept that what we need to understand is as how do we measure the deviation of a real gas from an ideal gas. Okay, now we need to understand how do we measure the deviation of the real gases from the ideal gases. So, in order to measure the deviation of the real gases from the ideal gases or from the ideal behavior, we take help of we do take the help of compressibility factor. So, compressibility factor is a factor which is been denoted by the letter as Z. Okay, now this particular thing, compressibility factor, is nothing more than a ratio. A ratio of pressure into volume product to the nRT. So, this particular thing, this particular expression is nothing more than a compressibility factor. Okay, so using the compressibility factor for a particular gas, and let's plot a graph of compressibility factor versus the pressure. If we do that, what we are going to get is, we are going to get over here, let's say this axis is going to represent to us a Z axis. Okay, so it is going to represent to us a compressibility factor, and let's say over here, let's say over here, we are going to have a pressure axis. Okay, so when we do plot a graph of the compressibility factor versus the pressure, let's say if we are going to have an ideal gas. So for an ideal gas, this particular volume, this particular value, that is Z is equal to PV over nRT for 1 mole should be equal to 1, or I could call it as a unity. That is, it is going to remain constant, and if that is so, then we shall plot it over here like this. So this would represent to us our ideal behavior. Okay, so this will show us an ideal gas plot. Okay, so but when we do plot the same type of graph for a real gas, as we have already mentioned that no gas is going to be absolutely real. Okay, that means there are going to be deviations. There are 2 types of deviations which are usually observed. One, either this particular plot is going to go on the top, something like this, or either the plot is going to go at the bottom, something like this. Okay, so when we do observe like that, then if the plot is going to the top, then we do call it as a positive deviation. Okay, and if the particular plot is going just something like a below the ideal gases, we call this as a negative deviation. Okay. Now, first let's observe the points for the negative deviations. So when we observe the negative deviations in a sense, here, of course, Z value for this is going to be less than that of 1 because it is going down. Correct. So here, compressibility factor value is going to be less than unity, and that is nothing more than less than 1. So here, can we say that? Therefore, P into V, that is for your real gases, is going to be less than nRT. Of course, when this particular value is greater, then only we are going to get the value of Z less than 1. Okay, so this is a condition as what we can get. Okay, so therefore, can we say that substituting value of nRT by P into V, but that of the ideal gas. Okay, so therefore, can we say that P into V of a real gas is less than P into V, the product into the volume of the ideal gases. So if this is a condition that is achieved, then can we say that the volume of real gas is less than the volume of the ideal gases? Okay, now what does this particular point mean to us? It means to say that these particular gases are more compressible than that of the ideal gases. Okay, so this is what it shows us. So whenever a real gas shows a negative deviation when we compare to that of the ideal gas condition, these are the gases which are more compressible. Okay. On the other hand, if we do observe the condition, as that of the positive deviations, so when we have a positive deviation, what is going to happen again? Here, Z, that is a complexibility factor, Z is going to be greater than 1. Correct, when it was lesser than 1, here it is greater than 1. So when we say greater than 1, that means P into V, that means this particular amount should be, of course, greater than nRT. This is for the real gas now. Okay, so again, substituting nRT by whom we are going to substitute now again is by the PV of ideal condition. So therefore, P into V of an ideal condition. So at this particular point, can we say that P into V as that of the real gas is of course greater than P into V of that of the ideal gas conditions. Okay, so again, what does this mean to us? It means that volume of a real gas is greater than the volume of the ideal gases. Alright. So, if that is a condition, then here, what is going to happen? As we have discussed with respect to the compressibility. Okay, these gases are more compressible. Okay, so therefore these are the gases more compressible. So if it is more compressible, that means the attractive forces between the two molecules is much more greater. So quite simple as in this particular cases, attractive forces. Here, the attractive forces are going to predominate. While in this particular case, as what we have seen already, is that the real gases volume is much more greater than that of the ideal gases. So therefore, these are less compressible. So when we say that these are less compressible, that means these here between the two molecules there is a greater repulsive forces. Okay, so here repulsive forces are going to these are going to predominate. Okay, so when we observe this all conditions, this positive deviation and negative deviation, how they do vary with respect to the volume and with respect to the attractive forces. So these are the only causes for our deviation. So I hope you have understood how do we do measure these particular deviations of the real gases with respect to that of the ideal gas. So majorly we have two types of deviation. One is either positive, one is either negative. If it is positive, compressibility factor is greater than 1, and if it is negative, compressibility factor is lower than 1. Okay, so this is how it all. Let us begin with the last concept for this particular video, and that is going to be the Boyle's point, or what we also call it as the Boyle temperature. Okay, in order to understand this, let us say that we are going to plot a graph for the nitrogen gas. Let's take into consideration of nitrogen gas. And let's plot a graph of Z versus pressure. Okay, now Z again compressibility factor. Correct. So when we do plot a graph of Z versus P, let's say this is a compressibility factor over here, and let us say this is our pressure axis. Okay, so for an ideal condition, let's first plot a graph for an ideal condition. Let's say this is the ideal condition as what we have. Okay, now when we do plot a graph for the nitrogen gas, okay, so when we do plot a graph of the nitrogen gas, what happens here is that we observe an initial dip in a graph, and this happens, okay, and slowly it will start to increase. Let's say this particular thing was taken at 273, sorry, let's say that this was taken at 223 kelvins. Okay, so as we increase the temperature, let's say the next one was taken over here at around 273 kelvins. Okay, so as we try to increase the temperature, the dip in this particular graph goes on decreasing. So naturally there is going to be one particular point where as we increase this particular temperature, we see that at a particular temperature the dip is minimum. At this particular temperature, nitrogen gas will start showing us the behavior which are almost like that of the ideal conditions at an appreciable long range of pressure. So the temperature wherein the real gases will start to show us an ideal conditions, or will start to show us the nature which are equivalent to that of the ideal behaviors. That particular temperature, we call it as the Boyle's temperature, or we call it as a Boyle's point. Okay, now let us continue with this point. Let us say that we have the compressibility factor, that is Z. Okay, now Z is equal to what we have it as P into V divided by N into R into T. Correct. Now, if this is equal to 1, then that will become as an ideal condition. Okay. Now, for a real gas, let's say Z is equal to P into V of a real gas. The whole thing will be divided by N into R into T. Am I right at this point? Okay. So if we do consider that of an ideal gas, so what we have? P as it is already equal to 1. Okay, so can we write it down as Z is equal to P into V, that of the real gas. The whole thing can be divided by P into V for an ideal gas, as P into V for an ideal gas is equal to N into R divided by T, because that was equal to 1. Correct. So therefore, can we write it down as Z is equal to V of real gas divided by V of an ideal gas. Okay, at this particular condition, okay, we can also define this complexibility factor with respect to the volumes now. So the volume of a real gas to the volume of an ideal gas is called as the complexibility factor. Okay, at that particular temperature and pressure. Okay, I hope you have understood all these concepts for today. Yes, do take care, stay home, stay safe. If there is any problem, you can message me.